So let's start the last chapter, chapter 6. The first section is just a series of techniques we're going to learn about. So nothing deep, it's good, but it's going to build towards something as we close out chapter 6 next week. So the first technique we're going to learn about is something called a dot product or an inner product. And what that is how two vectors relate to each other. So I'm going to use this vector 3, 1, and I'm going to do the dot product with it with vector 2, 3. Now, this is officially looks illegal. If you were asked to multiply two vectors together, we can't really do that. But a dot product, it's not really multiplying vectors together. We're going to end up with a final answer, but watch this. It looks pretty intuitive. If I said multiply, you would tend to just think, how about just straight across, and you'd be right. But you don't end up with another vector. You end up with a scalar. So here we go. 3 times 2, 6, plus 1 times 3. Got it? And so my final answer, the dot product, is 9. Doesn't mean a lot to us right now, but just that's how you calculate this. Now, if we're to officially multiply these the way that matrices could talk, if I called this, let's say vector u and vector v, if you were asked to multiply these together, that would be illegal. But what wouldn't be illegal is if you showed it like this. The transpose of u would actually look like, instead of a column, it's now a row. And v itself, it stays a column. And if you think of it like that, then we're back to our normal rules of multiplying matrices, which says row times column, 6 plus 3, 9. And there's that same result. So I'm just showing you the formal, official way that you could do this, but I think we're going to be fine just multiplying the way I showed. So that was 3, 1 versus 2, 3. Let me show you two more real quick. I'm going to stick with 3, 1 as my base vector, and let's now dot product with negative 3, 2. And let's notice something. So dot product straight across, negative 9 plus positive 2 is negative 7. So let's just call this out. The result of a dot product is always a scalar. Looks like it can be positive or negative. And a takeaway from this is, what's the meaning of this? There is something geometric about this, but the main takeaway I want you to notice is 3, 1 and 2, 3. The angle in between is acute. It's less than 90 degrees. That's what a positive dot product gives you. The second one was negative. What does that mean? Well, I did a dot product 3, 1 versus negative 3, 2, this one way over here, and that angle is clearly obtuse, bigger than 90. So, if you had to guess, what do you think we're going to get when we dot a vector with a vector that is at a 90-degree angle? Negative 1, 3. And I hope you've already guessed you're going to get a 0. If a positive dot product says the angle in between is acute, if a negative says the angle in between is obtuse, then a dot product of 0 says we have a right angle between two angles. And the term we're going to use is orthogonal. You can see that easily on a XY scale. If you saw the slope of this is 1/3, this one is negative 3/1, slopes opposite reciprocals. But what's powerful about this dot product is that you can do it with vectors that are hard to see. For instance, in R3, if I gave you, let's say 10, 4, negative 2, and dot it with 2, negative 4, 2. Are these angles at a right angle? Are these vectors at a right angle to each other? Yeah, I don't know, but let's quickly calculate a dot product. Get 20 plus negative 16 plus negative 4 adds to 0. Check, orthogonal. So that's a pretty slick move. So let's look at a couple of exercises you're going to be able to need to perform for your homework. Let me give you. So let's say this is our first example. Let's say u is negative 2, 3, and v is 3, 6. So you'll just be asked to perform some calculations. For instance, you may be asked to find u dotted with v over v dotted with v, and that becomes just a large scalar, and then you're going to multiply that times the vector v. So this is just training your brain to for something that's coming later in chapter 6, but this is just technique. So let's do this. What is u dotted with v? Let's see, that would be -6 plus 18 over, you can dot a vector with itself, so not a problem. So 3 times 3, 6 times 6, we got that. And then I still have, now we're not dotting it with this, we're going to clean this up and we're just going to scale it vector v here in a moment. So let's clean up this fraction. What do I have? 12 45ths, better known as 4/15. And if I scale that times 3, 6, and clean that up, my final vector ends up being 4/5, I believe, and 8/5. Good. So again, it's just giving you an expression using the dot product inside, cleaning up a fraction and scaling it like normal. All right, next example. You're also going to use this idea of how to find the length of a vector. That's sometimes referred to as the norm of a vector. And let's say I give you a vector v that is -50, +120. So what is the length of this vector in units? Well, you'll be asked like this. First of all, that's how it's vector v, and those double bars on either side is asking what's the length of this vector. And what you do is it's like the Pythagorean theorem essentially, which is you're just going to dot v with itself. So what is -50 times -50 plus 120 times 120? And like the Pythagorean theorem, the last step is square root that. And so it turns out if you plug those numbers in, work it out, the length of this is 130. That's it. Now there's a follow-up to this, is to then produce what's called the unit vector. So here's a vector heading in one direction. What vector has length 1 in that same direction? Well, it's an easy move. Once you've figured out the length of this vector is 130, what if I divide it by 130 and get it down to 1 unit? And that's how you get it. And what we'll do is we'll take the length of that vector and we'll not divide, but we'll multiply by the reciprocal of that and scale my original vector. And we'll clean this up. And so -50 over 130, better known as -5/13, and 120 over 130, 12/13. That is length 1 in the same direction as my original vector. Okay, last example. How do you find the distance between two vectors? So let's give you, let's say, vector u, 10, -6, vector v, -4, -8. So again, these two vectors are heading out in different directions, and what we first need to figure out is we're going to get in a sense, a vector between the tips of these two. So step number 1 is subtract these two vectors. Doesn't matter which order. So just say u minus v, and I get 10 minus -4. negative 6 minus negative 8. Okay? And then the distance between them is just the length of this vector. So we then ask for the length, which is the square root of 14 squared plus 2 squared equals square root of 200. And there it is. Just a quick reminder, in your online homework, you may be asked to give the exact radical form of this, so don't forget how to break up a radical into its final move. So if I break that into 100 times 2, the final best looking answer is 10 root 2. All right.